Well, hello everyone. My name's Richard Peck. I'm a clinical pharmacologist who now works with the Van der Schaar Lab and the Cambridge Centre for Artificial Intelligence in Medicine. And I'd like to welcome you all to this short video that I'm holding with one of the fourth-year PhD students working in the lab, Alicia Curth, who's part of the Department of Applied Mathematics and Theoretical Physics at the University of Cambridge in the UK. And with Alicia, we've recently published a paper on the topic of individual treatment effect estimation. And as a drug developer and a clinician, this was particularly exciting for me because I realized how, we're all, when we're treating patients, and as clinical pharmacologists trying to understand drugs, we're trying to understand really what to do for individual patients. And yet we have to do that using population data, which is really what randomized clinical trials are, the typical substrate of the data we're working on. But it feels to me like machine learning is advancing to a point where it can now really bring out the potential for being able to understand what the likely effect is in a specific individual and to use that to guide the choices we make about how to treat patients. And that's actually what this paper is all about. It talks to really some fairly specific areas of that, the methodology that, well, Alicia will tell us much more about, but as I understand it, is called conditional average treatment effect estimation. But, I think we will be seeing much more of this in our work and in our practice as drug developers and prescribers. And I hope you'll be interested to learn just a little bit more about it. So with that, Alicia, thank you for taking part in this little discussion. Can I start by asking just some basic questions? Maybe you could start by telling us what conditional average treatment effect, what CATE actually is, at least in your words.
Of course. Thank you, Richard. Also, thank you so much for the introduction. So in my work, I'm often interested in estimating conditional average treatment effects, or CATE, which is kind of another word for having individualized treatment effect estimates. So usually, I think in medicine and in randomized controlled trials, we look at population average effects, so effects averaged out over an entire population of patients. Whereas what we are interested in individualizing this a little bit more. So in estimating and treatment effect conditional on a patient's covariates, so on a patient's characteristics. So we allow for effect heterogeneity in estimation, and we want to have a look at what does the treatment do to a patient's outcome given the patient's characteristics, instead of averaging it out over the whole population.
And as I understand it from things you've taught me, really, as we've been working on this, this is not easy, or this is something that traditional machine learning approaches struggle with, perhaps. Again, would you be able to just say a little bit more about why that is? And then we'll move on to some of the newer approaches that you've been working on, for example.
Yeah, totally. Indeed, I think CATE estimation, or individualized treatment effect estimation, is in itself quite an interesting machine learning problem because it's very different from the problems that we usually look at in like the purely kind of predictive cat versus dog machine learning systems that we look at. And this is specifically because there's kind of some biases in the data that we observe in practice. And so machine learning is incredibly good at making predictions about the status quo from data. So if I were to treat patients in the exact same way that people in the data are already treating them, then I could make good a forecast with machine learning. But if we're thinking about treatment effects, what we're actually interested in is making interventions on the data generating mechanism. So it's about asking the question, what if I were to treat the patients differently to how I treat them right now? So kind of switching, this idea of switching on a treatment and switching it off. And that's very different from the purely predictive setting. So that makes learning treatment effects from observational data actually quite hard, because I need to be able to reason about what would happen to patients if they were treated differently as they are right now. So you can already tell by the language I kind of have to use here. This is a bit more of a complicated problem because it's hypothetical, right? There's some counterfactual reasoning going on here. And whenever there's kind of reasoning, just simply predicting from the data isn't really isn't enough. So what we really need is to make some assumptions on the data, like on the data that we've collected. We need to make assumptions that we have collected enough evidence to be able to even argue about counterfactual scenarios from this data. So I think this is what makes treatment effect estimation a very unique, it's kind of a very unique machine learning problem because you're much more dependent on the data that you have available to actually be good for the task.
And we'll come back to data later because I think it's going to be really important for people to understand what are there particular characteristics or what type of data is suitable and not suitable and so on. But just before we do that, I mean, the paper talks through some of the issues, if you like, some of the things, the watch outs, some of the things to be careful about when using CATE. Have you covered, is there anything else you want to say on that topic? Have you covered all the key points, or would there be any other points you would want to make in terms of things to be careful about and or potential solutions to those problems and how to deal with them? And after that, I'll ask you to come back to data.
Yeah, I think the one thing I didn't mention yet, and that's actually my favorite parts, like as a statistician, that's like my favorite technical part of the CATE estimation problem, which is there's something very interesting going on in that. So a treatment effect, conceptually, if you think about it, the effect of a treatment is always defined with respect to two outcomes. It's looking at what would happen to me if I were to be given the treatment, and I compare this to what would happen to me if I weren't given the treatment. So it's very much like a contrast between two outcomes, and that's very different from normal prediction problems. Usually, like if you think of like image prediction tasks where you give the machine learning algorithm an image and you either say this is a cat, like is this a cat or is this a dog? There's no such concept of like contrasting an effect, and that also means that the estimation problem, so estimating the difference between two functions, is a different problem than just estimating the outcome itself. And that makes the machine learning problem actually quite interesting because it means that so one way of estimating treatment effects is just to learn a model that predicts outcome with treatment and to learn a model that predicts outcome without treatment, and then to just kind of take the difference between the two and use that as a treatment effect. But it turns out that's actually not always optimal. And if you were to come up with a model that directly targets the difference between the two outcomes, that can actually do a lot better in practice. And I think that's my favorite part. Like as a statistician, like just technically speaking, that's very interesting because you can do a lot better. And like the machine learning literature has come up with ways of doing a lot better than doing like the naive thing by targeting it. And I think that's my favorite thing.
Well, thank you for that. So we do need to talk about data.
Yeah.
And I have two questions related to data. One is to ask, are there features that make a data set either more or less usable? And I know this is an impossible question to answer, but can you say anything about what sort of size data sets, particularly in terms of numbers of patients and amount of data per patient, might be needed?
So the first question was what kind of types of data or like what types of data sets would be useful. And so I think the most important characteristic of a data set with respect to actually being able to estimate any treatment effects from it at all is that we need to know enough about how treatment was assigned in the data. To ensure that there's actually no such thing as like hidden confounding, so that there's no confounding of the treatment assignment mechanism, because if you have that and you don't have the reason of confounding recorded, you have no chance at actually estimating good treatment effects. So one great way of getting rid of confounding is having randomized data available. So if there is sufficiently large data sets, so that will go into the second question, but if there are sufficiently large data sets from randomized studies, that would be, of course, be great, because in that case, you don't have to worry about hidden confounders being there being any confounders, because by definition, the treatment should be assigned randomly. Whereas then on the other hand, you can definitely learn treatment effects from observational data if you are kind of sure that you've measured all the confounding factors in it. And I think you kind of get to kind of a kitchen sink problem where the more you've measured in your data, the more columns you have on different patient characteristics that could potentially be confounders, the more likely you are to have captured everything that you want. But the more confounders you have, the bigger you need your data set to be as well. So you don't, like, the more columns you have, the more examples you need to be able to learn anything from the data. So I think that's kind of, that's the trade-offs there. I think a randomized study would be great if it's big enough, and observational data can be very useful if you are sure that you've measured what you need. And then to get to the question of what is big enough, it's a hard question. I don't think it's possible right now to answer that like as a blanket statement, because it very much depends on what kind of machine learning methods you're using and what kind of characteristics your data set has. However, like a rule of thumb is the more complicated the model is that you're trying to fit, the more data you're going to need. I think there are rules of thumbs that say something like you need about 10 times as much data as you have parameters in your model. I'm not sure to what extent these rules are still kind of defendable today. I think they're a bit older. But what I can say is that the machine learning literature, when they've developed these algorithms, they usually test them on some kind of data sets. And these data sets are usually of actually kind of moderate size. So we're talking about like 1,000 to a couple of thousand examples. So they're not huge. So moderately sized phase 3 type trial data sets might even be an option. And I think the kind of the rule of thumb for me would be the larger the data set, the more individualized a model can you actually fit.
Okay.
Because you can still, I guess you can still allow for some heterogeneity. If you have smaller data sets, it might just not go all the way to the individual level. You might have to restrict yourself to kind of defining smaller and smaller subgroups, which at some point become individual, but might not be possible on the basis of all data sets.
Okay, thanks. I appreciate the answer. I know that's an impossible question to give a clear answer to, but thank you very much for what you did. So, final question, hopefully there will be people who are interested to either find out more or to actually try developing a model for estimating CATE based on a data set they have. What would you advise people who want to learn more or have a go to do?
I hope they will want to read the review that we wrote.
That would be a good start.
Yeah, exactly. So check out our CPT paper because we do survey the challenges, opportunities, and a lot of the solutions that do exist in this paper. And this includes some of my own work as well as the broader methodological work of our lab, so the Van der Schaar lab here in Cambridge. And there is also quite some posts on our own website that maybe we can link here on our more like methodological work in more detail that we've done in the lab. And yeah, I think going from there and looking at the work that we have done, but also there are a lot of other machine learning labs working on these kind of problems. And also this is like heterogeneous treatment effect estimation has also become a bigger topic in econometrics and biostatistics. So we link to a lot of the work in our review. So I think there's a lot of literature and a lot of very interesting methods. And we hope we have now linked kind of a new target audience to this literature, which is usually targeted at different at different people. But we hope that this will find its way into the more mainstream medical literature now as well.
That's great. I actually really like the point that there may be a lot we can learn from other disciplines, completely different disciplines.
Exactly.
From medicine and from pharmacology, with like the econometrics area and so on, for whom some of these problems may be new for us, may be a bit less new for others, and they may have found solutions that we can adopt and build on. That's great. Alicia, thank you so much for putting up with my questions and for doing this video. Really appreciate you taking the time. And to everyone who has listened, I hope this was useful. Thank you very much for your attention.
Thank you.
and goodbye.